Hi everyone, Mrs. V here, and today we are going to learn how to calculate the rate of a chemical reaction. So let's get our PowerPoint on and let's start learning. By the end of this video, you will be confident to calculate reaction rates using data tables or rate curve graphs. So let's get into it. Some chemical reactions are really fast. An example of this would be explosions, while others are actually quite slow. For instance, the rusting of an iron chain. But fast and slow are qualitative descriptions of reaction rate. To be able to calculate how fast a reaction is going, we need to be able to observe something changing during the course of the chemical reaction. And there are several reactions in which we can study the rate of reaction quantitatively. One of the properties that's used to study the rate of reaction is the mass of the substance, and this is particularly useful for reactions that produce gases. As the gas escapes from the flask, the mass of the flask is going to decrease. Let's have a look at the reaction between hydrochloric acid and marble chips. Marble chips are calcium carbonate, and of course when a carbonate reacts with an acid you get water and carbon dioxide produced, and that carbon dioxide can escape from the flask. As the carbon dioxide escapes from the flask, the mass will decrease. The mass of the flask can be recorded at regular time intervals, and we can actually graph that against time in this graph here. It produces a graph called a rate curve. You could also plot the mass of carbon dioxide that was lost. All you'd need to do was subtract each mass from the starting mass, and you could find the loss in mass and graph that. So these graphs that are produced are called rate curves, and we can use them to calculate the rate of reaction. This can also be done if you have a gas syringe. You can collect the gas that's evolved in a reaction that produces a gas and measure its volume. A rate curve can be drawn for any property that changes during a reaction. Some chemical reactions involve gradual colour changes. For instance, the reaction of potassium permanganate with oxalic acid. Potassium permanganate is a deep magenta colour. As the potassium permanganate is used up, the colour will fade. A colorimeter, or the proper name for that is a spectrophotometer, can measure the amount of light that's absorbed by the potassium permanganate and give you a quantification of the colour change over time. You can actually use that data and plot a rate curve. Rate just means how much change there has been in a certain amount of time. We can calculate the average rate of a chemical reaction by looking at the change in the concentration of substances. Now, usually concentration is used, but you could use anything. You could use mass, you could use volume, you could use absorbance for colour changes, and the units that you use for the rate of reaction will just depend on what you actually used. So if you used mass, you'll get, say, grams per second. If you used volume, you might get mils per minute. This will not give you the rate at a specific time. It's going to give you the average rate over the time interval. So at the start of the time interval, the rate will be higher than the average, and at the end of the time interval, the rate will be lower than the average. Let's look at an example. We've got a data table here that shows the volume of oxygen gas that's been produced in a reaction where potassium chlorate has decomposed to produce oxygen and potassium chloride. So we're measuring the volume of the oxygen that's being produced. And we have here a data table that records the volume of oxygen that's been produced every 30 seconds. Let's calculate the rate of reaction during the first 30 seconds. First of all, our property is volume, so our units of volume are mils, and our units of time are seconds, which means that the units for our rate will end up being mils per second. So our average rate is just the change in volume over the change in time. Now, if we look at the 30-second mark, we see that the volume is 10. If we look at the 0 mark, the volume is 4, so the change has been 10 minus 4. The change in time has been 30 minus 0. If you run that through the calculator, you will get 0.20 mils per second. If you want to write that more scientifically, you can write that as mils per second. Your turn now. For that same data set, I want you to calculate the reaction rate between 60 seconds and 90 seconds. We'll be back with the answer in a minute. So your average rate is the change in volume, which is 21 minus 16, divided by the change in time, which is 90 minus 60. If you run that through the calculator, you'll get 0.17 mils per second. It's much easier to see what's happening to the rate of a reaction as the reaction proceeds if we actually graph that data into a rate curve. We can tell from the gradient of the rate curve how fast the reaction is. Let's have a look at our mass of carbon dioxide produced versus time graph, and we see at the start of the reaction, the graph is very steep, the gradient is large, and that shows that the reaction's occurring at a very high rate. As the reaction proceeds, we see the gradient is less steep. The reaction here is now slowing down. And finally, right at the end, we see that the graph is horizontal, so our gradient is 0. That simply means that the reaction has now stopped. No more carbon dioxide gas is being produced. The reaction is over. We've run out of reactants. The rate curve allows us to calculate what's called an instantaneous rate of reaction. So rather than an average rate of reaction over a time period, we're looking at a rate at a particular time. And all we need to do is calculate the gradient of the tangent to the curve at that particular time. A tangent is just a line that touches the curve at one point only, and it shows the same gradient as the curve has at that point. Once we've drawn a tangent line, we can triangulate that line and calculate the gradient using rise over run. This can be done for any point at the reaction. For instance, at t equals 600 seconds here, we've drawn a tangent to the curve, we triangulate it, and we use rise over run. If you've already studied some calculus, you'll be able to use differentiation to calculate the gradient of a tangent. But if not, then you're going to need to manually construct that tangent. For this, you're going to need a protractor and a sharp pencil. The first step is to construct a normal to the curve. That's a line that's perpendicular or at 90 degrees to the curve. So you're going to line your protractor's 90-degree line up as close as you can get to the slope of the curve. So here's your 90-degree line. And you're going to make sure that your protractor is lined up with, here we're taking the rate at the 3-minute mark. So you're going to line your protractor up there. Then if you draw a line along the straight edge of the protractor, this is going to give you the normal to the curve at t equals 3 minutes. Now you're going to want to turn your protractor around so that the 90-degree line is lining up on the normal. Then you're going to draw a line that just touches the curve along the straight edge of the protractor, and that is your tangent to the curve. Once you have your tangent, you can construct a triangle to give you the rise over the run. Here I think my rise is about 40 minus 20. And my run is 4 minus, I think this is around about 0.2. And so now I can calculate the gradient of that tangent. If I run that through my calculator, I get 5.3 grams per minute. I got my units for loss in mass, grams, and minutes for time from the axis labels on the graph. Well, I hope you feel a lot more confident now about how to calculate the rate of reaction. If you found this video useful, please give it a like. And of course, if you want to learn even more about this wonderful subject of chemistry, then please subscribe to my channel and watch some more videos. I'm going to see you guys in the next video.